All right, so let's talk about some of the different models that were proposed for the structure of an atom. Rutherford was one of the first ones to come up with the you got to start somewhere, right? And you got to give this guy credit because he just said, well, maybe all the protons and electrons just kind of hang out together in this sphere, and the charges cancel each other out. That's why it's neutral. Maybe that's it. This is called the plum pudding model, sort of like a sea of positive plums and positive pudding, and maybe the electrons are the plums. I'm not sure. I've never actually had plum pudding. So he theorized that this would be the structure. And then he had to test it. And this is a really cool experiment because it's just so far ahead of its time. He aimed a positive beam of positive charges at a sample of gold. And he said, okay, what do I see when this happens? And basically, I won't go into all the details. They're in your book. But what he saw was that there's this scattering of charges. The beam passes through the plum pudding and makes little flashes of light along this zinc oxide screen. However, what he saw was not consistent with his proposal that positive and negative charges are just kind of coexisting in a random fashion in the middle or in the nucleus. He didn't see that at all. He would have expected that a positive charge, because of the randomized charge distribution, that it would just pass through unperturbed, but that's not what he saw. He saw that because of this scatter, he said, okay, there must be something else going on. And then he proposed something that's going to start to look a lot more like the atom that we know and love today, and that is, he said, maybe all the positive charges are in the middle, and the negative charges somehow hang out along the perimeter. And then if you aim a positive beam, well, if the positive beam, when it hits the positive charges, positive and positive repel each other. So these are going to be the ones that scatter. And there's a much better drawing than this in your textbook on page 212. However, the positive charges that are aimed at the outer edges, where there are currently negative charges, then those are not going to be deflected, and so those are going to pass through. So you're going to get these bouncing off, and then some passing through. And it's a little convoluted, but basically that's what he saw. So the data supported not the plum pudding theory, but I think he called it the planetary, what did he call it? The idea that there are protons and electrons go around the protons. All right, at this point in the textbook, it seems a little incongruous. We start talking about light, wavelengths, colors. It doesn't seem to go with the structure of the atom. And I'll admit, the first time I thought, why are we talking about light in this chapter? But it has to do with the experiments that were done to first elucidate the structure of the atom. They needed to know a little bit more about the nature of light. So that's why your textbook stops talking about protons and neutrons and it starts talking about light. So let's review what we probably already know about light, and that is we have this particle-wave duality. Somehow light is both composed of particles and also it has a wave function. It acts like a wave, but it's made of particles. So this very cool sort of mind-bending theory. So I'm looking at starting on page 213 when we start talking about light. So the basic stuff that we need to know about light is that, let's draw just a basic light wave on the board. This will look familiar. It's a very familiar mathematical form. It looks like a sine curve or a cosine curve. What you need to remember is that when you draw a wave like this, there are certain parts of the wave that you can label. We call this a crest. We call this a trough, the high point and the low point of the wave. The distance from one crest to the next is called a wavelength. We're going to use lambda to represent our wavelength. Okay? The other thing you need to know is called amplitude. Amplitude is measured right here. So the wavelength, or the distance between two successive crests or two successive troughs, is super important when it comes to the color of light. Wavelength determines color. On the next page, on page 215, you see a pretty rainbow at the bottom of the page, and it says the visible spectrum. And you can see that red, orange, yellow, green, blue, indigo, and violet range from 700 nanometers for red down to 400 nanometers wavelength for violet. So there are several questions in your book that require you to determine what color a light is if it has this many, if its wavelength is this many nanometers long. Okay, so the other thing is if wavelength corresponds to color, amplitude corresponds to brightness. Okay, let's see here. Also, light waves move. So you've got a speed factor in there too. What is the speed of light? 3 times 10 to the 8 meters per second, or 9.8 times 10 to the 8 feet per second. This is called a constant, and we'll represent that with the letter C. Speed of light. Okay, so you need to be able to use that in a couple of different formulas. The first formula that we're given is something called frequency. Frequency has to do with that speed. How fast, if you picture a little guy standing over here, how fast, if these wavelengths are moving towards him, how fast is he going to be hit by successive waves is one way to look at it. How many waves per second? The formula is frequency equals the speed of light divided by the wavelength. I'll write that down. There's our constant, C. And remember, lambda is going to be our wavelength. Let's talk about units. C, or the speed of light, is in meters per second. Lambda is going to be, it's usually given in nanometers, but you got to make sure that you're using all the same units, so you'd want to convert your nanometers to meters. And then so you've got meters per second on top and meters on the bottom. Meters per second times 1 over meters. Whoa, what a weird unit. What do you get? If you divide this by this, you get 1 per second. You could also write that as second to the minus 1. That's strange, but that's what it is. So this 1 per second unit, or seconds to the minus 1, is also called a hertz. So your answers will be in hertz. Okay, let's try to do one. Let's look at on your own 7.4. What color is a light that has a frequency of 6.4 times 10 to the 14 hertz? So we're going to use this and just plug in the numbers. That's what's given. Some kind of light that has a frequency of 6.4 times 10 to the 14 hertz. You know the constant, the speed of light. And you're trying to solve for lambda, which is the wavelength in meters. So if you want to solve for this, you got to rearrange it. You're going to have to use your algebra knowledge. You can, there's a number of ways to do it, whatever works for you. I tend to say, well, if I want lambda, I'm just going to mentally move lambda over here. Actually, I'm going to actually move lambda over here. By multiplying both sides of the equation by lambda. And now I can solve for lambda by dividing both sides by this number. So I'm going to get 3.0 times 10 to the 8 meters per second divided by 6.4 times 10 to the 14 hertz, which is 1 per second. Now, notice here, if I'm dividing meters per second by 1 per second, that's the same as meters per second times second over 1, which is going to give me my answer in meters, which is right. So again, the units can help you check to make sure you're setting it up and rearranging it algebraically in a correct fashion. Okay, so we want our answer to be in meters. And what is it going to be? Lambda is going to come out to be, I don't know, 4.7 times 10 to the minus 7. Okay. Now, that's in meters. The little chart in your book that tells you what color the different wavelengths are is in nanometers. So I would suggest changing this, converting this to nanometers. So I'm going to move up here. 4.7 times 10 to the minus 7 meters. How many nanometers in a meter? 10 to the minus 9 per meter. So we've got that's your conversion factor. So if you do that with your calculator, you should get 470 nanometers.